Hello everyone who is watching this record of the presentation. My name is Pozhylenkov Alexei. I am PhD student from the Odessa National Meshnikova University, and today I want to discuss on the topic of my PhD project, the stress state of an elastic rectangular domain under the steady load. Here is the structure of my report. Firstly, I want to make a brief literature review. Second, I will introduce the problem statement that I am working on. Next, show how I have solved this problem, what mathematical approach I have used, how I have found the solution in the transforms domain. Next, I will show some numerical results. And the last one is the conclusion notes. So let's begin. The problem of the elastic rectangular domain is not a new one, but unfortunately a lot of unsolved issues remain. This problem was considered and resolved in the different statements important to the engineering applications as with the help of the analytical methods, and with the numerical ones. The well-known paper was one of the pioneer papers in this direction. The solution of the plane thermoelasticity problem for a rectangular domain was constructed with the help of the new solvent method. This method permits the construction of an analytical solution corresponding to the Saint Venant principle in the form of trigonometric series expansion, using a complete orthogonal set of the eigenfunction and associated functions. These investigations were successfully continued by uh, the second paper. To the direction one can reference the papers where the boundary element free method was applied to two-dimensional problems of elasticity. This method is direct numerical method, and it was stated as the third paper, gives the higher computational accuracy. For example, at the fourth paper, the discussion of the conditions type necessary for the penalty methods to provide a basis for the stable and convergent finite element schemes is proposed. But if one need to provide the calculation of the stress and the rectangular domain in the neighborhood of the angular points, the numerical methods lose their efficiency as it is known. So the main idea of my research is to find the exact and analytical solution for the sum of the problems of the elasticity for the rectangular domain. And the novelty of the presented solution is to apply methods which were stated by the Popov Gennady and described at the fifth paper. So here we have the elastic rectangular domain. We consider it in such way that x changes from 0 to a, and y changes from 0 to b, and t changes from 0 to infinity. The first two lines are well-known equations of elasticity that is stated for the two-dimensional problem. Our domain meets a lot of the upper face of the domain. It is equation 2. The lower base as a condition of ideal contact, it is equation 3. The right side as the condition of the ideal contact, it is equation 4. The left side also as a condition of the ideal contact, it is equation 5. Here we consider the case of the harmonic vibrations for the variable t. So the original statement of the problem is derived in the following form. To solve it, I have applied the Fourier transforms, which can help to rewrite our stated problem in the one-dimensional field. Here is presented the detailed representation how I have applied this method. It is equation 11. You can see that I have applied two different Fourier transforms for the displacement functions, but with the same eigenvalue. So as a result, we will have a one-dimensional problem that I have derived in the matrix vector representation, presented in the equations 12 till 15. Here it is, the detailed matrix definitions which are used in the matrix vector boundary problem. To find a solution for the one-dimensional boundary problem, I have used a fundamental solution matrix, which is solution of the homogeneous problem. I have found it in such form, which is represented in the equation 16, where to calculate such integral I have used well-known residue theorem. So as a result, we have two parts of the fundamental solution matrix. It is equations 18 and 19. Thus, we have found the solution of the homogeneous one-dimensional vector boundary problem. Here it is the definitions of the matrices E0 and E1. The last step for finding the exact solution of the one-dimensional problem is to find the unknown coefficients C1 to C4, applying the boundary conditions 15 to the solution matrix Z. The linear system has been obtained for the coefficients. So here is the system. So the final exact solution of the displacements of our problems we can find just applying the reversible Fourier transform. Here it is, the final representation. So here it is some numerical results with the stated load function px. On this picture you can see that the numerical results has done with the t equal to 0 and frequency equal to 0.01 for the whole rectangular domain. On this picture we have the same function as we had on the previous one, but with the t equal to 200 and with the same value for the frequency. Finally, let's to sum up. What has been done? Has been solved the dynamic elasticity problem for the rectangular domain under the steady load. The exact solution was derived in the explicit form, and numerical investigation was done for the different values of frequency and geometrical size of the domain. The future research will lead to the considering the dynamic elasticity problem with the conditions of the second main problem of elasticity at the lateral sides. Thank you for your attention.